Okay, 2.5 is set identities. So a set identity is an equation involving sets that is true regardless of the content of the sets. In the expressions. So it's going to be true regardless of what numbers or what sets are in the sets. Okay, so some set identities. Let's list them out. Okay, we'll have the name and we'll have the identities. Okay. Okay, the first name is going to be, the first identity is the idempotent clause. And this just says that if I take A and I union it with A, I get A. And if I take A and I intersect it with A, I get A because they're the same thing. Let's look at the associative laws. Okay, A unioned with B unioned with C is the same as A unioned with B unioned with C. Okay, it doesn't matter which one I do first, I'll end up with the same result. Okay, the same is true of A intersect B intersect C is the same as A intersect B intersect C. Again, the order of the intersection doesn't matter. Okay, the commutative laws. Okay, is A union B is equal to B union A, and A intersection B is equal to B intersection A. Okay. Order doesn't matter there. Okay, let's look at one that's a little bit more interesting, the distributive laws. Okay, if I take A and I union it with B intersects C, that is the same as doing A union B intersect A union C. Okay. Also, if I take A intersect B union C, that is the same as A intersect B unioned with A intersect C. The identity laws are A unioned with the null set is A, and A intersect with the universal set, okay, is equal to A. So this is universal set. Okay. I take A with everything, intersect, I get A. If I take the union of A and nothing, I get A. Okay, so if I take A with everything, intersect, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of A and nothing, I get A. If I take the union of Okay, domination laws. Okay, is if I take A and I intersect it with the null, I get the null. If I take A and I union it with the universal set, okay, I get the universal set back out. Okay. Double complement laws, okay, is if I negate A and then I negate it again, I get back A. The double complement law. Should just be a law there, not laws. There's just one of them. Okay. Okay. The complement laws are if I take A and I intersect it with A naught, I get nothing. Okay. If I take A and I intersect it with A naught, I get everything. Okay, universal set. If I negate the universal set, I get nothing. And if I negate the null set, I get everything. Okay. Those are the complement laws. Let's talk about the De Morgan's laws. So De Morgan's laws are A union B complement is equal to A complement intersect B complement. So if I negate A union B, I get the negation of A intersected with the negation of B. Okay. If I take A intersection B and I negate it, I get the negation of A unioned with the negation of B. Okay. Okay, and then the absorption laws. Okay, so if I take A union A intersect B, that's just A. B basically gets absorbed. Okay, if I take A intersect with A union B, that's A, and A gets absorbed. Didn't matter what B was. We kind of threw B out because of the way the sets work. Okay, let's do a proof of one of these De Morgan's laws. Okay. So let's do a proof. Example 1. Prove A intersect B is equal to the A intersect B complement is equal to A complement union B complement. So let's prove this.
All right, Professor, can you scroll up just a bit? Just so you can get the last laws really quick. To the very top, I'm so sorry. Um, just a little bit more. I missed the first couple. My connection's kind of bad. Um,
Couple. You want me to go all the way back?
yeah, perfect. I'm just gonna take a picture really quick. My
Okay.
connection was kind of okay. Thank you so much. I really appreciate that.
Okay. Okay. So let's prove this statement. Okay, so let's look at the proof here. Okay. Okay. So I'm going to say that there are statements and there are justifications. Okay, statements and justifications. Okay. Statement is that A intersect B complement. And this is just, our given statement. Okay, number 2. Okay, not the negation of X an element of A and B. And that's just the definition of complement. Okay, is that we're negating the intersection of A and B. It's the negation of it. Okay, number 3, okay, is that we're going to negate X an element of A and X an element of B. We're going to intersect those in A with those in B. And that's just the definition of intersection. Okay, number 4. Okay, this is going to then become the negation of X an element of A unioned with the negation of X an element of B. There shouldn't be there should just be element there, element of B. Okay, and that's your typical De Morgan's law from logic. So we're taking this idea of sets, and we're applying logic to the sets. That's the regular De Morgan's law from logic. Okay, number 5. Okay, X is an element of A complement. Okay, unioned, not union anymore. It's not a union. It's a okay. It's using our logic operator. Okay, it's our conjunction. Okay, so we're taking it from our set operators of intersection and union, and we're turning it into our conjunctions and disjunctions. So this is now a conjunction using, okay, now we're going to go back to the idea of sets. Okay, this is a conjunction. Okay, X is an element, okay, of B complement. Okay, so that's definition of complement. Okay, and the conjunction of the complement of A with the complement of B, okay, now is the union. Okay, X is an element of, X is an element of A, the complement of A unioned with the complement of B. Okay. And that's from the definition of union. Okay, therefore, okay, and maybe we'll go back to, we'll do number 7 here. So 7. Okay, 7. Okay. And we'll go to just A. A union B, A complement union B complement. That's just okay. That's just a definition of domain. So we want to take all of the x's. Okay, and so we built a bridge from the given to what we want. So therefore, A intersect B is equal to A or A intersect B complement is equal to A complement union B complement. Okay. And we can close off the proof there. Example 2. Okay, we want to prove that A intersect A intersect C complement is equal to A intersect C complement. So we want to use all these laws, set laws, to help us do that. Right? So let's do that. So again, statements and justifications. Right? So number 1, A intersect C complement. Okay, and that's just my given expression. Okay, number 2, A intersect A complement union C complement. What is that? What did I use there? Yeah, this is a thing that we just proved. I used De Morgan's law. Okay, De Morgan's laws for sets. Okay, number 3. I'm going to go A intersect A complement union A intersect C complement. What did I use there? What did I do there? Yep, thank you, Eric. Distribute. Okay, distributive law. Okay, number 4. If I take A and I intersect with A complement, I get nothing. Okay, and that was the complement law. Okay, complement law. Okay. Number 5. Okay, A intersects C complement union with the null set. What did I do there? Yeah, that's the commutative law. Okay. And then 6, okay, we have A intersects C complement, because when we union something with the null set, it is itself. What's that mean? What's that law? Yeah, thank you, Anna. It's the identity law. The identity law. Okay, and that is that's 2.5.